So this subject is the calculation of normal stress and shear stress in the arbitrary directions. Click the 1, 2, 3, 4, 4th step on top of my lecture note. Then you can, clicking this tab leads you the subject that we consider. So again, we want to consider one-dimensional member here. This is subjected to a pair of forces on both sides. So now at this moment, probably you guys understand very well the calculation of normal stress in the normal direction. So let's imagine an arbitrary plane here, P and Q. And then here the P and Q, the cross-section PQ is inclined by angle theta here with respect to the longitudinal direction of the member. Then here we want to calculate the normal stress and shear stress on this surface. So if angle theta is equal to 0, so we call the surface normal stress, isn't it? The calculation of normal stress is very easy, isn't it? We already know that the normal stress is equal to applied force P divided by the cross-section area. So if you consider this inclined surface PQ, then because the surface is inclined, and then here the area is greater than the reference area, isn't it? So if you consider this area, this is the smallest area. So if you consider inclined surface, this area must be greater than this area, isn't it, right? So if you want to calculate the traction on this surface, so we have to divide. So I want to call this area is A theta. As I told you, A theta is greater than A naught, the reference area. Okay. So now let's try to calculate the magnitude of this traction. This traction on this surface is equal to applied force P divided by the length A theta. Okay. So let's compare the normal stress sigma naught and the traction P theta here. Then make sure that P is same. Okay, P is same in the both relation. And then but here, by the way, A naught. So A naught is less than A theta, which means traction on this inclined surface should be less than, its magnitude is less than the normal stress sigma naught. Okay? Because area changes. But by the way, these two equations satisfy the force equilibrium completely. So now we want to talk about the situation on inclined surface. So here I have, let's imagine that we have inclined surface. Okay. And then we always consider normal. But this is my normal now. My normal. And then the direction of the normal is characterized by this angle theta, normal vector. Okay, so in this member, so we want to consider this coordinate system x here. So now we want to consider another coordinate system because we are talking about what happened on this surface. That's why here I'd like to introduce a coordinate system following the right-hand rule. So x theta and the y theta. As you can see, my coordinate system have been rotated by angle theta, isn't it? That's what we want to do. But what's the reason that we want to consider this new coordinate system? Because we are very familiar with this Cartesian coordinate system. That's why for any discussion what happened on this inclined surface, so we want to consider new Cartesian and orthogonal coordinate system So where we want to discuss the normal stress and the shear stress. Okay, to do so, we have to decompose the force. So this is the original force, external force, into two different components. The normal component and then the shear component, V. So this is nothing but a vector decomposition. Then here the normal force magnitude is nothing but the projection of force P by angle theta. That's why P times cosine theta. And how about shear force? V, the magnitude of V, make sure that the angle is given by this arrow. That's why we only calculate the magnitude V. The V is P times sine theta. Make sure this is a sine theta. Okay. So now let's work one by one. So how to calculate normal stress for this? So normal force divided by this area is equal to the normal stress in that direction, isn't it? So that's why what we want to do is I'd like to calculate the normal stress by dividing the normal force by this area, okay? So here the area, as I told you, the cross-section area, reference area divided by cosine theta. So you can consider another way. Say I have such an area. The cosine theta, this area is equal to A naught. That's why this area is equal to A naught divided by cosine theta, because of geometrical relation. Now let's calculate the normal stress in theta direction. The normal force divided by area theta. So normal force is given here. So P times cosine theta. P times cosine theta, 1 cosine. And then area, if you look at the area, I have another cosine. That's why I have cosine square theta here. So if you use half angle theorem, so I wonder if you're familiar with half angle theorem. And then here P over A naught is replaced by sigma naught. And then let's use half angle theorem. Then cosine square theta is written by a half 1 plus cosine 2 theta. This is a half angle theorem. in 우리말 삼각함수 반각정리라고 그러죠. 반각정리. And then how about the shear stress in this direction? Shear stress in this direction. What I mean? Where is it? Shear stress in this direction. Where is my coordinate? Oh, here. This is my coordinate, isn't it? Shear stress in this direction. So if you do that, so we have to divide the magnitude of shear force divided by the area, then it's gonna be equal to the shear force is given by P times sine theta, P times sine theta, and then I have one area. Somebody's cutting me. Then A naught divided by cosine theta. That's why here we have P sine theta and cosine theta. Let's replace P over A naught by the normal stress. Then we have normal stress here and also here. And then I have information on trigonometric functions. So by the way, make sure that why we have the reason that why we have minus sign here, because the direction of traction is opposite to the default direction of my coordinate. Look at this. The default direction of my positive shear stress is given by y theta here, okay? But it's going the opposite direction. That's why we put the minus sign. Is it clear? That's the only reason, okay? So if you want to use different coordinate system, the sign must conform to the choice of coordinate system. So nothing is confused, okay? Nothing to be confused. Okay, so let's look at the trigonometric function. So what's going to happen if angle theta is equal to like pi over 2, 45 degrees. The pi over 2 is equal to, but is that produce cosine pi over 2, and pi over 4, if you 45 degrees, then the cosine 2 theta is equal to cosine pi over 2, this is equal to 0. Then it's gonna be sigma naught is equal to a half sigma naught. Is it correct? Yeah. And then tau, how about tau theta? The tau theta, if you put a pi over 2, then we have a square, a half 1 over square 2, and also 1 over square 2. Then we must have, you know, a half of sigma naught 2. Okay, so let's look at here. So if you consider 45 degrees, as I told you, we have the normal stress component, a half of sigma naught reference stress, and the shear stress also, I have a half of it. Okay, if you put the different directions, then we have different values of normal stress and shear stress. That depends on the angle. And this angle is called angle of observation, okay? Angle of observation. 관찰각. Okay, so let me stop my lecture here today. Next subject is deformation energy. Deformation energy of structural body. Actually, this chapter is very important. I recommend you to read my lecture note in advance before coming to my classroom. Here I'd like to summarize, I'd like to provide you most of essential information regarding the energy issues. So I'm very sure that if you take my lecture regarding the deformation energy carefully, you don't have any problem to accept other issues related to the energy principles. So let me stop my lecture here today. Thank you.